Welcome to another lesson of sectoral structures theory. This particular lesson is a little bit outside of the book, but it is helpful in that we will talk about what happens when we restrict the weights of a given sectoral structure to specific values, and how does this affect the combinatorics of those sectoral structures. But we will walk through an example and then we will try to extrapolate this to other values. So the weight restrictions we will use in this example will be 1 and 2. So that means we will only look at sectoral structures whose parts are made up of either 1 or 2 sectors, because that's what we specified. We will use this notation of the set brackets basically to indicate the values that we want to restrict or the weights that we want to allow. And then after we close the set notation, we will put a sectoral structure, in this case yn. And what we mean by that is actually the set of sectoral structures of degree n whose parts have weights that are restricted to the values between the brackets that are indicated. So for example, if we do this, 2, 3, closed brackets, y6, then that means we are talking about the sectoral structures of degree 6 whose parts are restricted to 2 and 3. Additionally, we will introduce this notation of we put the restricted or the allowed numbers or digits within the set notation, followed by a bracket with a number in them. And in this case, this is sort of similar like we saw with the meme function. We would say meme followed by n. So in this case, what we are saying is we want the size of the set of degree n whose weights are restricted to a and b. So let's look at an example. So if I say 4, 6, 7, close the set notation, open brackets, 11. So this means we want to find out the size of the set or the total number of sectoral structures of degree 11 whose parts are made up only of 4, 6, or 7, or a combination of these. So finally, the last notation I want to introduce is this reflexive arrow here. It looks like the refresh symbol on an internet browser. And if you see this followed by a specific sectoral structure, let's say 3, 2, 1, this indicates, so there's an arrow just to distinguish it from other symbols. So this indicates all possible sectoral structures that are rearrangements of these particular digits. However, they have to be sectoral structures. So we will call them sectoral rearrangements. So when you see this symbol, this indicates all sectoral rearrangements of the specified digits. Notice that for this symbol, it could have something like 2, 1, 1, 1. And in this case, we want to look at all these sectoral structures that have 3 1s and a 2. Okay, so now that we got the notation out of the way, let's quickly go over this example. So again, we are looking at sectoral structures whose weights are restricted to 1 and 2. And when we say we open the set brackets, 1, 2, yn is a subset of Stn. STN is the set of all sectoral structures of degree n, and in this case, this is only the subset whose parts are made of 1s and 2s. For example, let's say we want to look at the set 1, 2 of y subscript 4. This means we want to look at all sectoral structures of degree 4 that are made of 1s and 2s. So this includes 2 squared 4, subscript 4, 2 1 squared subscript 4, and also a rearrangement of that, which is 1 2 1 subscript 4. So I could simply write one of them, preferably this top one, and precede it by this symbol, which means all rearrangements of 2 1 squared 4, followed by 1 to the 4th subscript 4. Now, if I write it in this notation, the set 1, 2, open brackets 4, that means I want the size of this set, and that size is equal to 4. Another example, 1 to y subscript 5. This includes 2 squared 1 subscript 5 and its rearrangements, 2 1 cubed subscript 5 and all its rearrangements, and finally 1 to the 5th subscript 5. Similarly, we say the set 1, 2 of degree 5 is equal to 5. So that means the size is equal to 5. So in this case, they're both equal to n. However, this is a coincidence, as we will see in this next one. So we want all sectoral structures of degree 6 whose weights are restricted to 1 and 2. So we have 2 cubed subscript 6. We have 2 squared 1 squared subscript 6 and all its rearrangements, which gives us a total of 4. We have 2 1 to the 4th subscript 6 and all its rearrangements, and there are 3 total. And then we have 1 to the 6th subscript 6. So therefore we say the size of the sectoral set of degree 6 restricted to weights of 1, 2 is equal to 9. So as always, we like to figure out what is really going on with these sets. So we will divide them into odd and even, as is always the best way to start. So for even degrees of n, we will say that the set of sectoral structures of degree n, where n is even, whose weights are restricted to 1 and 2, is of the following format. 1 to the power of n subscript n, there's one of that only. Next, we're going to introduce a 2, and then we have to reduce the power of n by 2. So we will say 2, 1 to the n minus 2 and all its rearrangements, followed by 2 squared, 1 to the n minus 4 in this case, and all its rearrangements. And we keep doing this until we reach 2 to the power of n minus 2 over 2, 1 squared, subscript n, and finally 2 to the power of n divided by 2, subscript n. So notice, if we were looking at degree 6, this would be 2 to the 3rd subscript 6. So this is what that is. If the degree is odd, it looks slightly different. If the degree is odd, then we start the same exact way, 1 to the power of n subscript n, and we keep moving. Once we reach the end, it starts looking slightly different because we started with an odd degree. So we end up with the very last one will be 2 to the power of n minus 1 divided by 2, 1. Subscript n, all its rearrangements. Now let's take a minute to look at what we mean by all its rearrangements. So if we have 2, 1, subscript 3, how many possible sectoral structures can we make? It's really just one sectoral structure. So all the rearrangements of this, there's only one of them. If we look at 2, 1 squared subscript 4, there's 2 possible ways to rearrange those and get a sectoral structure. If we look at 2, 1 cubed subscript 5, there's also 2. And quickly we notice that there's a pattern. If we have a sectoral structure 2, comma 1 to the n minus 2, subscript n, the total number of rearrangements for this sectoral structure is simply the floor function of n divided by 2. So it's pretty easy. Now, what about if we look at the ones that start with 2 squared instead of just 2? So there it starts to be a little bit, just one layer of complexity higher. So we want the form 2 to the power of 2, or 2 squared, comma 1 to the power of k, subscript n. In this case, k is equal to n minus 4, so that it adds up to n. And the total number of rearrangements for something like that, where it starts with 2 squared, comma 1 to the power of k, is n minus 2 squared divided by 4, and we take the floor function of that. So again, pretty straightforward relatively. Once we reach the third power of 2, things are not as clean anymore, and we have to do some real combinatorics at that stage. So let's look at the general formula for all the possible rearrangements for a sectoral structure of the form 2 to the power of, we put x, 2 to the power of x, 1 to the power of y. Subscript n. Notice n in this case is equal to 2x plus y. So 2x plus y is equal to n. So how many possible rearrangements do we have? Basically, this is similar to figuring it out for the mean function, but at a smaller degree. So we want first all the possible permutations of this, and then we want to add to it the symmetric sectoral structures, and then we divide it all by 2. So basically, a sectoral structure version of the Burnside lemma. This gives us 1/2 of the following: x plus y factorial divided by x factorial, y factorial, and then plus, notice this expression here, this either gives us a 1 or a 0. So sometimes you'll stop here, sometimes you'll continue. So we'll say 1 plus negative 1 to the power of x times y divided by 2. So this expression means we either use a 0 or a 1. And multiplied by the floor function of x plus y over 2, and then factorial of that, divided by the floor function of x over 2, take the factorial of that, times the floor function of y over 2, and we take the factorial of that. And you can stop the video just to try and think through this, basically by figuring out the total number of permutations, which gives us this, and then the total number of symmetric structures, which gives us this, and then we add them together and we take half of that expression. Um, so, if we look at all sectoral structures of degree n, or the set of all sectoral structures of degree n, whose parts are made up of only ones and twos, it is equal to the union of all the substructures, or sorry, not substructures, the subsets of sectoral structures of degree n and parts and order I, from I equals 1 to I equals n. When does I equal n? Basically when we have a Xi structure, so 1 to the power, in which the order is equal to the degree. Additionally, we can say this as the union of all sectoral structures of the, or of all rearrangements of all sectoral structures of the form 2 to the a, comma 1 to the n minus 2a subscript n, starting with a equals 0 and ending with the floor function of n over 2. So this is really a key statement. Let me say it again. We're starting with this general form 2 to the a, comma 1 to the n minus 2a. We start with a equals 0. So this gives us nothing here, and then 1 to the n. And we keep increasing a until we reach the floor function of n over 2. So this is all the possible sectoral structures that satisfy these criteria. And then the size of this set, we'll say 1, 2, the set 1, 2, and then of degree n is equal to half, which is basically another way of looking at this same thing, of the sum of n minus a factorial. What is n minus, where did we get the n minus a? It's basically adding a plus n minus 2a. So that's x plus y. N minus 2a plus a is n minus a. Factorial over a factorial n minus 2a factorial. This is the same expression as this. From a equals 0 all the way to the floor of n over 2, plus, and the half is outside of this, plus, this is another way of saying this one function, but because I don't just have an x and y cleanly here, I'm going to say 1 unless x is odd and n is even, then this equals 0. So for it's always 1, but if x is odd and n is even, then this becomes 0 and this goes away. Otherwise it stays, and it equals to n minus a over 2 floor function factorial divided by a over 2 floor function factorial times n minus 2a over 2 floor function factorial. So this is the same thing as this. Take a minute to see that these are really the same thing. So this long formula can help us figure out the size of any sectoral set of degree n whose parts are restricted to 1 and 2, or whose weights are restricted to 1 and 2. We could stop here, but there's something very interesting. And that's why I wanted to show you this example, because as we go forward in sectoral structure theory, the Fibonacci numbers will keep appearing over and over for us. So one observation that we will notice is the following. I'll start with this simpler version of it. The size of the sectoral set of degree 2n, so 2n, whose weights are, whose sectoral structures have weights restricted to 1 and 2, is equal to half of the Fibonacci number of 2n plus 1 plus the Fibonacci number of n plus 2. So this is a very beautiful and simple relationship. So for example, if the degree of the sectoral structure was 20, instead of plugging it into this very intimidating formula, we will say, instead of 20, we will say 2 times 10. And we will say this equals to the Fibonacci number of, this will equal to half of the 21st Fibonacci number plus 10 plus 2 is 12, the 12th Fibonacci number. So F21 plus F12. And then if it's an odd number, we express it as 2n plus 1, and we say 1/2 of Fibonacci number 2n plus 2 plus Fibonacci n plus 1. So if I have here the, let's say 101, and I want to know how many sectoral structures of degree 101 have weights made up of only 1s and 2s, you'd think this would take a long time, but all we have to do is say half of F 102 plus F of 51. So F, the 102nd Fibonacci plus 51st Fibonacci. A different way, if you don't want to use 2n and 2n plus 1 and you just want to use n, it gets a little bit uglier. So there is a direct formula we can use also using Fibonacci numbers. We would basically say that for if the degree is n, regardless of whether it's odd or even, the total number of sectoral structures restricted to 1 and 2 will be half of Fibonacci n plus 1 plus the Fibonacci whose order is floor of n divided by 2 plus 3 plus negative 1 to the power of n divided by 2. However, I find it easier to just express it either as 2n or 2n plus 1. The sequence we get is found, is a documented sequence for these particular sectoral structures, and the sets are of the following sizes: 1, 2, 2, 4, 5, 9, 12, 21, 30, 51, 76. And we can see this sequence again well established in a very different context though. Thank you.